Hey everybody, so here is your last video in this particular unit, last video of the semester actually. And so this kind of goes along on the heels of all the other things that we've been doing in this unit. This one has to do with recognizing some different types of chemical reactions based on their chemical equations. And this is something that you can do to help you balance equations, really helps you predict products, which is something we'll end up doing a little bit more in the second semester. And it's just one of those kind of chemistry things that you should be able to do. Our last, the big PowerPoint slide deck that you guys need to do is all about finding examples of different types of reactions like this. So that's what this is meant to do. This is going to give you an overview of kind of what those reaction types are. If you've got that worksheet out, the one that's about balancing equations, you'll notice that each of the sections in there is one of these types of reactions. So it'll help you kind of recognize it as well. You may want to have that out somewhere nearby as we're going through this. So again, with this, it's just a way to kind of organize your thinking and kind of get your head around some of the different ways that reactants can form products. Sometimes they come together, sometimes they break apart, sometimes they make more complicated things, sometimes they just switch partners. Lots of different things like that. We're definitely oversimplifying this. There's lots of other ways that we can classify chemical reactions. I'm going to call the 5+1 or the 6 types of chemical reactions. There's definitely more than that. I'll give you the bonus redox type here at the very end if you're interested in that higher level. But this is just one way that reactions can kind of get categorized. So again, it's just one style. So if you don't want you to sit there and think that, well, Miss Benwell said there are 6 kind of reactions. Well, yeah, in this particular system, there's other ways that we can classify them as well. So with this, here's our list. And again, if you've got that worksheet of balancing chemical equations, here's the 6 or the 5+1 types of chemical equations. There's a couple of ones where there's some other synonyms. Like if you Google these, you may find some other names for it. Synthesis and decomposition are pretty commonly used. Single displacement is sometimes known as single replacement. Double displacement is sometimes known as combination. And then combustion is simply fire. And then the other type is dissociation, which is kind of not really a chemical reaction. It's actually a physical process, but it underlies a lot of other things that happen in here. And then the last one that I'll talk about at the very end is a 7th type, which is called redox. And redox kind of crosses all of these different combinations here. So it's its own style of classification. So there's when I'm talking about the 6 different types of chemical reactions, that's what I'm referring to. Synthesis and decomposition, I'll talk about those two kind of together. Single displacement, double displacement, I'll talk about those two together. Combustion's kind of its own thing, and then dissociation is kind of its own thing. So there's our 6 different types of reactions. So for this one, I'm going to start off with synthesis and what synthesis reactions are. Oops, my picture of me is covering that up. There we go. Move that over to the side. So with this, I'm going to hide that. There we go. With synthesis is exactly what it sounds like. You're synthesizing something. The word actually means to build something bigger or to build something new. So typical synthesis reactions have some very simple reactants, like just a single element and another single element, and then in the reaction they get smushed together to make a new product. So you can kind of see I've got some examples down here. I have a Homer Simpson example. Spider pig, of course. Spider pig does whatever a spider pig does. With these, typically what you're going to find in synthesis reactions, you're starting with something simple and you're making something more complicated. That's what a synthesis reaction is. The simplest ones are like this top one and this bottom one here, where you have an element plus an element and you're forming a compound. This bottom one here, element plus element, forming a compound. Again, it does not matter that it's diatomic or whether it's metallic, where it's a single element. You still have zinc by itself and iodine by itself. And then here on the right side, you're forming the ionic compound, zinc 2 iodide or sodium chloride. This middle one is a slightly more complicated version of a synthesis reaction, where you have a small reactant and a second small reactant, and you're smushing these together to make a single bigger reactant. So this was calcium oxide reacting with water or hydrogen hydroxide to form calcium hydroxide. So again, with these, you've got 2 simpler things to make a single thing. Typically with synthesis reactions, you have 2 things on the left. Oftentimes it's element plus element, and then you typically have one product, which is a compound on the right. So that's a synthesis reaction. The opposite of synthesis reaction is what we call decomposition reactions. If synthesis is to build up, then decomposition is to break down. This is Beethoven's favorite type of reaction, because this is what Beethoven is doing right now. Beethoven in life, of course, was a composer. But now that Beethoven is dead, he's a decomposer. No? Okay, anyway. So had to put one shitty joke in here. Come on, guys. So decomposition, literally with these, it's the opposite in style of a synthesis reaction. In these, you're going to start off with a single product, or sorry, a single reactant, and then it's usually breaking apart into two simpler products. So usually it's a compound on the left and two elements on the right. Usually, not always 100%. My cartoon version of it, it's the Flintstones version of it. We've got a combination here on the left. It's a compound. And then we have our two single elements present on the right. So you can kind of see this one. This got alumina is a kind of a casual name for aluminum oxide. And then if we run some electricity through it, we get aluminum and oxygen gas. So we've got a compound, which is Al2O3, and it breaks apart into aluminum atoms and oxygen molecules, I guess, because it's O2s. Here you can see a slightly different version of it. This is the decomposition hydrogen peroxide. Hydrogen peroxide, you've got this in your house. It's in a brown bottle at your house because simple light, just regular bathroom light, is enough to break it down like this. And if you leave hydrogen peroxide out in a glass on the counter, it will literally break apart into water and oxygen gas. So in this particular case, again, you've got one compound on the left, and it's breaking apart into a compound and an element on the right. In this case, the compound that it's producing is simpler or smaller. So again, in each case here, you've got one thing present on the left, one single compound on the left, and it's breaking apart into two simpler things on the right. Oftentimes they're single elements, but they could be two simple compounds on the right. Okay, moving on from decomposition. These get a little bit more complicated looking, but try not to panic when you see these. So this is called single displacement. Single displacement is also known as the I'm going to get your girl kind of equations right here. So you can kind of imagine we've got an element and then a compound. So you have a single individual and then you have a couple. You can kind of see my dancing friends down at the bottom here. And what happens here is that one individual displaces something from the partnership. In this case, this dancing dude kicks out the other dancing dude. It doesn't necessarily make him unhappy. I don't want you to think about it as like breaking up a relationship, because you can see that our dancing friend here is perfectly fine. If you take a look at what's happening in this more symbolic reaction here, A is going to kick out or displace B, take its place. And so we see now B gets kicked out and ends up by itself. And now A is got the partner of C. So again, C stayed with a partner both times. A displaced B and B got kicked out is kind of how we do this. Whenever we do these sorts of reactions, a metal will always displace another metal. In this case, hydrogen is acting like a metal. It's a positive ion, cation. So you've got a cation, zinc, kicking out another cation, hydrogen. So the zinc kicks out hydrogen and ends up with chlorine. So here's your afterwards. Now the zinc and chlorine are together, and then the hydrogen has got kicked out on its own. Why do we have this change in some of these subscript numbers? Those change in subscript numbers come from the chemical formulas, from the ion charges. Remember, zinc's a 2+ and chlorine's a 1-. So that's where that's coming from. And hydrogen, when it's in its elemental form, hydrogen gas is a diatomic gas. So that's why it ends up by itself. Here you can see another example of iron and copper are switching partners. The iron is going to displace copper and end up with sulfate. So we start off with iron by itself and copper with sulfate. And when we're done, we have copper by itself and iron with sulfate. And you can kind of see the charges on here where that happens. So these are called single displacement or single replacement reactions. I did not show any examples in here, but it is possible to do these with a gas displacing another gas or a non-metal displacing a non-metal. Typically in Chem 1, we reserve it to these metal displacing metal types of reactions where one metal, iron, is kicking out a second metal, copper, and taking in its girl, or taking its anion, so to speak, and moving on from there. All right. Next type of reaction that follows up is something that we call double displacement. Now, instead of just having one thing jumping in, we actually have two things that are switching partners. And I'll tell you the story of the pool party here in just a second. But rather than one thing kicking out from a partner, we literally have two things switching places. Two different compounds are swapping partners. So in this particular case, we had A and B started off, and then C and D started off. And you can see that A and C swapped partners. And so they end up with now C ends up with B, and A ends up with D. Here's why this is called the pool party. I'll tell you the lame story. I don't want to take too long in video form like this. Imagine a pool party. Imagine a bunch of you guys are getting ready to go to a pool party. The reason why I talk about a pool party is because a lot of times these reactions are done in solution, i.e. dissolved in water. So that's why we're going to call this a pool party. But imagine you and your partner show up in one car, and somebody else, and a friend and their partner show up in a different car. Maybe it's kind of like the little Mario friends down at the bottom. The two princesses show up in one car, they're together, and then the two Marios, Mario and Luigi, show up in their particular car together. And then when we get to the pool, everyone just all jumps in and separates. So A goes its own way, B goes its own way, C goes its own way, D goes. Everyone starts intermingling and talks to one another like, hey, we're all having a great time. We're all dancing around. Everything's amazing. You get to see all of your good friends, and you spend a bunch of time kind of hanging out, mingling for a while. This is called dissolving or dissociation. And I'll come back to that at the end. But all of these individuals kind of get thrown in the pool together, start swimming around. And then occasionally, and this happens from time to time at the pool party, sometimes some of these pairs see one another and they're so into each other that they literally fall out. This is called precipitation, is what this is called. But literally, they bond together so tightly that they're no longer just mingling anymore. So I don't know which of these two pairs that you want. These two look like they're a little bit closer together. So maybe these two all of a sudden just amazingly start off and decide that they are just completely into one another. And so they yay, these guys are together. So now these guys bond together, but these guys, maybe they're just sort of friends. They like each other, but maybe they're not quite into each other like these guys are. So these could maybe form some sort of a new product. And this was what kind of drives that reaction, is that certain of these ions, these new combinations of cations and anions, sort of fall in love with one another. And that's the pool party. And they literally leave the pool party. They're like, dude, I'm out. And then who's left behind is whatever other ions are still present that's on here. So, for example, I know from some of these ones that are up here, maybe who would happen. So like in this particular case, magnesium and chloride show up together in a single car. Those guys were friends to begin with. And potassium and hydroxide showed up together. They're friends to begin with. But when we put them all in the pool together, some new combinations, some new introduction can be made. And it turns out that I happen to know that magnesium and hydroxide, oh man, these guys, once they meet, they are so into each other that they literally form a white little powder, and they literally just fall to the bottom, and they literally just completely leave the chemical equation entirely. But what about potassium and chloride? Well, potassium and chloride are still there. They're still swimming around in the party as well, but they're not quite as into each other. Similar things can happen with all of these, where you can see that H and Cl came together, and then sodium and hydroxide came together. Helps if you think about this in terms of words. And then the new partners, it's almost like foil, like inside outside is kind of like who the new possible partners are. The two insides are sodium and chlorine, and then the two outsides would be hydrogen and hydroxide. And hydrogen hydroxide is known as water, HOH, hydrogen hydroxide. Down at the bottom here, we've got potassium nitrate and Ki. So again, inside outside is usually the new combinations, how we can predict who's going to meet with who. So lead and iodine end up together, and here they are. And then we'd have our two inside friends together. This would be potassium and nitrate would end up together, and there those guys are. So when we end up doing our products for these, you always have one positive and one negative one together. These look super complicated, like I said, because you have so many different ions, and then there's all kinds of subscript numbers and things that are happening all over the place. These can be really confusing, but again, what I find for students is it really helps if you think of it in terms of the words, hydrogen and chlorine, sodium and hydroxide, and you switch the first and last names inside outside, or lead and nitrate, potassium and iodine, you switch the first and last names. So you get lead and iodide, and then you get potassium and nitrate, and that's kind of an easy way to predict what they are. So there's two special categories of these double displacement reactions, and I mentioned them on the previous page there. One type of double displacement reactions that we do a lot, we actually did this earlier in the year, I don't know if you remember this lab, where we would put together combinations of solutions that were maybe clear to begin with, and then they would turn some sort of a funky color and it would kind of get cloudy. These are called precipitation reactions. This is the fancy name for this. Precipitation, or PPT, is a commonly used abbreviation for these, is when two clear solutions that were containing a bunch of ions will form a solid as a result of this. And for this, you need to use something called solubility rules. In a longer unit, we spend a bunch more time with this. We'll come back to this later on in the year, so I'm sort of previewing it. But you try to figure out what would be our new product. So if you think about this, again, we do inside outside. Potassium and nitrate, our two outside ones, end up together. Potassium and nitrate's one of our products. And then our other one would be lead and iodine, and this would be Pb, and it's I2 because I happen to know that lead forms lead 2, and its iodine is a 1-. Again, I know that Pb is a 2+ ion from looking at nitrate, which is a 1- ion. So there you go. And then if I want to know which one of those actually formed this yellow stuff that's up here, I would use something called solubility rules to figure out which of the things would form a solid. There's a shortcut rule called NaCl-NoSo. That's what this stands for. These things are not PPTs. These things are the things that are soluble. These are the things that dissolve. Anything with sodium dissolves. Anything with chlorine generally tends to dissolve. Anything with NO or nitrate tends to dissolve. And anything with sulfate, SO, tends to dissolve. At NaCl-NoSo is a kind of a trick. So if I take a look at this, I know that this one right here is soluble. UBLE. Hi, cat, orange cat. And then I know that this one, because it's not covered in NaCl-NoSo, this one right here is going to be our PPT. It's the other one. So again, if you're wondering, I'm not going to test you on this. I'm going to test you on writing and balancing equations. I'm previewing something that we're going to see later on. So again, double displacement reactions, precipitation reactions, or formation of solid is one of the important types of this. A second one that's also a double displacement reaction is what we would call acid-base reactions or neutralization reactions, where we take an acid and a base together and they form salt and water. When I put the word salt here, I'm putting the word salt in quotes. Salt here simply means an ionic compound. It can be any sort of thing, O-U-N-D. What you guys know of as table salt is a type of salt, but it's any sort of an ionic compound that can be formed from an acid and a base reaction. Acids always start with hydrogen, so we've got two different acids here. This one's hydrochloric acid, this one's sulfuric acid. And then we have over here two bases. Bases commonly have hydroxide in them. That's one easy way to recognize an acid and a base. But these are double displacement reactions, so we have inside-outside. So if you think about what our outside here, our outside would be hydrogen and hydroxide, also known as water. And then our two insides would be the sodium and the chlorine, NaCl. And that's what you guys would know as being table salt. But again, it's just a double displacement reaction that happens to form something that's called a salt. In this case, this is a soluble salt. So you know that salt is dissolvable. And then this other product, instead of forming a solid, is actually liquid water. If you do this right, and don't try this at home, seriously, it's dangerous. If you take hydrochloric acid and sodium hydroxide and you mix them together in exactly the same concentration, that's the key. That's why I don't demonstrate this. But if you mix them together at exactly the same concentration, they would literally neutralize and you'd end up with nothing but just salty water when you're done. It tastes kind of gross because it's just salty water. But that's literally what you make from it. Completely neutralizes the acid and the base. For a sulfuric acid example down here, again, it's inside-outside. We have hydrogen ions and hydroxide ions, forms HOH. And then our other two is the potassium and the sulfate end up coming together. Potassium and sulfate. I'll remind you the potassium is a 1+ and sulfate's a 2-. So it's actually K2SO4 is the final product that's made from this particular thing. And then we could go back and balance our equation if we want to. But this is still water. And then potassium sulfate is called a salt. And it actually does kind of taste a little bit salty. Sulfates don't taste as salty as things like chlorides do, but it's still called a salt. So there you go. Double displacement reactions. Inside, outside, you're taking the two cations basically and switching which partner that they're with and making a couple of new combinations. You could make a precipitate, or you could make liquid water and salt in an acid-base reaction. Okay, our almost last one here is something called, what do we call this one? Combustion reaction. You guys know what combustion is. Combustion reactions are reactions where it forms fire. So I want to be really careful about this. Combustion in chemistry has a real particular meaning. Not everything that looks like it's on fire is a chemical reaction. Or sorry, I should take that back. Everything that looks like it's on fire is a chemical reaction. But not everything that looks like it's on fire is a combustion reaction. Combustion reactions have a very particular style in a chemistry context to make it combustion, not just fire. So in combustion reactions, it's always exothermic and you always get this production of heat and light and all that stuff that we call fire. But there's always a real kind of consistent sequence of events in combustion reactions. Number one, you always have O2 as a reactant. It doesn't need to say it. If it says I'm going to combust lighter fluid, or if I'm going to combust gasoline, you know that one of the reactants is always O2. Got to have oxygen gas. Always, always, always. The other reactant is going to be some sort of a carbon and hydrogen and maybe oxygen sort of thing. It depends on the reaction, though. This is kind of variable. So like you can see in this one, we've got up here, CH4 is the reactant. This is methane or fart gas. But you can see it's just carbon and hydrogen as opposed to glucose. We're talking about cellular respiration. Glucose, C6H12O6. See how this has got carbon and hydrogen, and this one also has oxygen to it. So you're going to always have a second reaction with carbon and hydrogen, and then maybe or maybe not oxygen kind of combined in there. But again, you can see with both of these, there's oxygen, O2 in both of them. And then your two products are always the same. It's one of the nice things about this. Easiest reactions to predict the products. Always CO2 and H2O. You can write it as H2O and CO2 is fine. But always CO2 and H2O are always your two products. That's always, always, always what you get. So combustion reactions, it's some sort of carbon, hydrogen, maybe oxygen. Always oxygen as a reactant. Always CO2 is one product. Always H2O is the other product. And that's what a combustion reaction is. You also get a production of heat and light as a result of this, and that's what we call fire, the plasma that's produced from there. Just so you know, as an FYI, when you balance chemical equations or combustion reactions, these tend to have the highest coefficients. They can be really kind of annoying to balance. And then when you're balancing them, don't start with oxygen. Generally, you want to start with the carbon and the hydrogen, balance those guys, and leave the oxygen for later. And then again, I want to remind you that not all things, like when you're burning, say, fireworks, for example, that's a different type of a synthesis reaction, really, rather than a combustion reaction. So it's a slightly different style. So again, combustion, they're actually really straightforward. It's always something carbon and hydrogen plus O2 produces CO2 plus H2O every single time. Last two kind of bonus types of reactions here I want to mention, just because they are kind of important in the context that we're doing. So number one is the type of reaction that's not really a reaction, that's called dissociation. So dissociation is literally the technical term for salts dissolving in water. It looks like a chemical equation, and you can write it like a chemical equation. But really what you're doing is you're just talking about separating something into ions. And this is dissociation is the balanced equation for when something dissolves. So literally, when you take a look at all of these, they have a similar sort of a process, and you can kind of see one down here as well. That if I have a reactant, it looks like a decomposition reaction. It's kind of what it looks like, but you can see the decomposition down below here. The biggest difference between dissociation and decomposition is that dissociation is literally just dissolving. And when you're done with these, you always end up with ions. Notice how this says H plus and this says Cl minus. All of these ones in these examples up here, hydrocyanic acid is HCN, hydrogen cyanide, and it dissolves into hydrogen ions and cyanide ions. Ammonium hydroxide, NH4OH, that's ammonium hydroxide, separates into ammonium ions, NH4s, and hydroxide ions, OHs. Mercuric chloride, it's a lovely name, mercury 2 chloride. We get HgCl2, that's mercuric or mercury 2 chloride, and it separates into mercury ions and chloride 2 chloride ions. So again, dissociation is literally just dissolving into water. It is not decomposition where it's turning into atoms. So if hydrochloric acid were to decompose, we would literally form hydrogen gas and chlorine gas, not hydrogen ions and chlorine ions. I know it's a small sounding difference, but it's actually kind of important in terms of what they are. Dissociation is actually a really key part of double displacement reactions. So like if we take HCl, hydrogen chloride, and potassium hydroxide, this is literally what it's happening, is it's actually when we put these in water, this is our pool party that I mentioned earlier, we've got hydrogen ions and chloride ions, and then we've got potassium ions and hydroxide ions, and these guys are all splashing together in water. That's what dissociation actually is. And then sometimes the magic occurs, like in this case, liquid water starts to form. They literally form that new thing, or a precipitate might form. And then these guys might stay just friends splashing around in the water. So dissociation is the +1 reaction. It's not really a reaction. It's a physical process, just separating into ions. But again, it looks like a chemical reaction. We can write it like a chemical reaction. And it's actually kind of behind a lot of the other chemical reactions that we do. So dissociation is the 6th type. And this last thing I'm about to do now is bonus reaction. You don't have to do this. If you're like brains full already, hit pause right now, hit stop. The last type of reaction is something called redox reactions. And redox reactions are something that actually overlaps a lot of other categories as well. So this is not something I'm going to test you on, but it's something that's actually kind of important because redox reactions are all about the transfer of electrons. And electrons, especially when we transfer them through wires, is what we call electricity. There's these types of reactions, redox reactions, actually drive A lot of different really important chemical reactions. All of your living types of reactions that you do biochemistry are all redox reactions. In your batteries, any type of battery that you use, sorry, batteries down here, those are always redox reactions. And then there's lots of other ones that don't even look like redox reactions that actually have the same thing that's going on underneath it. So these types of reactions, synthesis, decomposition, single displacement, double displacement, combustion, a lot of these actually involve redox underneath. Again, it's not always obvious. So how do you find out if it's redox or not? Easiest way to tell if a reaction is redox or not is you want to look for an element that's changing its Facebook status, so to speak. If it's by itself on one side, and then it's an ion, it's either got a positive or negative charge, and it's in a compound on the other side. Change in Facebook status is redox. So if it's single and then it's in a relationship, that's redox. If it's in a relationship and then it becomes single, then it's redox. A lot of these count as redox. If you take a look at synthesis, here we've got element A, single, element B, single. And then when we bring them together, they're now in a relationship. That means they've changed their status. Synthesis is a redox reaction. Decomposition reaction, here they are together, they're in a relationship. And then afterwards, we've got single and single. Again, this is a change in Facebook status. This is a redox reaction breaking up. Single displacement. Okay, is this redox? So here we have the red and the blue one are in a relationship, and green is solo. So this is a compound, red and blue, and then green is an element form. It's by itself. And on the other side, what we see has happened is all of a sudden there's a change in Facebook status for one of these. Red does not change. Red was in a relationship on both sides, both before and after, but green has changed. Green went from being a single atom to now being an ion. It's in a compound. So therefore, if green is changing, then it is definitely participating in redox. And then if we take a look at blue, blue is also participating in redox. Blue was in a compound earlier, and now it's solo by itself. It's on its own, and so therefore this is also redox. We always see two different things that are changing in here. One will go into a relationship and one will come out of a relationship or something like that. So in this case, both red and blue were participating in redox. Both green and blue were participating in redox. The red was just sort of a spectator. Red's relationship status didn't change as a part of this one. Okay, double displacement is double displacement redox. So here we've got red and blue are in a relationship, and then green and purple are in a relationship. And then afterwards, we take a look at now green and blue are in a relationship and red and purple are in a relationship. So did anybody's Facebook status change? The answer here is actually no. Everybody was in relationships before and everybody's in relationships afterwards. It doesn't matter that they're in different relationships. They have not actually changed their Facebook status. In a relationship, still in relationships. The only kind here, this one, double displacement, is not classified as being redox. Double displacement is just dissociation reactions where they're finding new partners, but they're not changing their actual status. They're not going from element to atom or ion to atom kind of compound. And then combustion. So combustion can be a little bit confusing for students. Here we've got carbon and hydrogen together. Here we've got oxygen. Now oxygen is diatomic, I know, but oxygen here is considered to be by itself. This is considered to be in its atomic form, no charge. This is its elemental form. And then here you can see oxygen has changed its status. It's not oxygen with itself. Oxygen is now with carbon, and then oxygen here is with hydrogen. So a combustion reaction is definitely considered to be a redox reaction. In fact, you can see the redox. That's what the heat and the light, the flame is that the energy that's coming out from this particular reaction that actually causes the fire. So in terms of what these are, this one's redox, this one's redox, this one's redox, this one's not redox, and this one's redox. So you can see that redox actually overlaps a lot of these other categories. And again, how can you tell? If you've got an element that is by itself on one side, and then that same element is in a compound on the other side. Again, oxygen can be kind of the confusing where the diatomic gases were. Here it is by itself here on the left, and then it's in compounds on the right. Then you know it's redox. So there you go. That's our overview of our different types of reactions. So it's our 5+1 types of chemical reactions, plus the bonus redox, plus dissociation, which actually isn't a chemical reaction at all. So there you go. I hope that kind of helps you understand some of the different types of reactions. And I hope that'll help you finish up your final project so that you can do well. There you go. So spread some kindness, not corona, right? And I will see you guys hopefully sometime after this. There you go. Have a good one. Bye. Bye, you guys. How do I get it to stop recording?